Imagine you're standing on a busy city street. Beneath your feet, 30 meters down, a subway train is rushing through a concrete tube at 80 kilometers per hour. Now imagine an engineer walks up to you and says, "We could never build that tunnel any deeper. Not because of the money, not because of the machines, but because of mathematics." That sounds almost impossible to believe. We live in an age where we've drilled through mountains, bored tunnels under entire oceans, and landed robots on Mars. Surely we can just dig a little deeper. But here's the thing. The ground doesn't care about your budget or your engineering ambition. And when you understand what's actually happening beneath the surface, the physics, the geometry, the invisible war between pressure and structure, you'll realize that this isn't a technological failure. It's a mathematical wall, and nobody gets through it. Let's start from the beginning. The soil and rock around that hole have been sitting there under pressure for millions of years. Every meter of earth above pushes down on every meter below. This is called overburden pressure, and it increases roughly with depth. The deeper you go, the more weight is sitting on top of you. Now, for tunnels with a depth of more than 4 times their diameter, constructed using a tunnel boring machine or drill and blast method, the pressure from surrounding ground acts almost equally from all sides, not just from above, but from the sides too. This is what engineers call a deep-buried tunnel condition, and it changes everything about how you design the lining, the concrete shell that holds the tunnel open. Here's where the mathematics gets uncomfortable. The lining is the main structure of a tunnel, used to withstand the pressure of surrounding rock, and its thickness directly represents its load-bearing capacity. Makes sense. The more pressure pushing in, the thicker your ring needs to be. But here's the trap. As you go deeper, ground pressure increases, so you need a thicker lining. A thicker lining means the inner diameter of the tunnel, the actual space the train uses, gets smaller. So you need to start with a larger hole to maintain the same usable space. But a larger hole means even more ground pressure trying to collapse it, which means you need an even thicker lining, which eats more of your diameter, which requires an even larger initial hole, which creates even more pressure. You see where this is going? It's a spiral, and it doesn't end. With increasing tunnel depths, the distribution and magnitude of ground pressure acting on the lining changes dramatically, and the calculation of ground pressure depends directly on the depth of the tunnel. There is a theoretical depth at which the required lining thickness equals the tunnel's own radius. At that point, you have a solid concrete cylinder with no space inside. The tunnel has eaten itself. When an underwater tunnel is excavated, groundwater flows in, especially when the infrastructure is located below the water table. The effective stresses around the tunnel are then affected by seepage forces. This is called hydrostatic pressure, and just like overburden pressure, it increases with depth. Every meter deeper you go, water pressure adds roughly 9.8 kilopascals to the force pushing against your lining. At 100 meters down, you're dealing with water pressure alone of nearly 10 atmospheres. Your concrete ring is now being squeezed by both soil and water simultaneously, from every direction. Tunnel structures are susceptible to complex groundwater and geological conditions, and in some special cases, it may be challenging for conventional lining to ensure the safety and stability of tunnels in the long term. This isn't a theoretical warning. This is what engineers have actually experienced on real projects. Arsenina station in Kiev is currently the second deepest metro station in the world at 105.5 meters, and its construction was a nightmare. The station was constantly flooded by underground waters despite its exceptional depth, which was originally intended to prevent flooding. Think about that. They dug deeper specifically to escape water, and the water followed them down. To prevent the construction from caving in, the soil had to be frozen. Around a reinforced concrete ring weighing more than 3,000 tons, approximately 400 wells were dug and filled with liquid nitrogen. Liquid nitrogen, just to keep the dirt from collapsing while they built the tunnel. and the escalator ride from platform to surface takes a full 5 minutes, equivalent to descending a 32-story skyscraper. That station works, but it is the outer edge of what is structurally viable with current materials, and it required extraordinary measures just to exist. A study published in the Bulletin of Engineering, Geology and the Environment by Springer Nature, examining the Tabriz subway project, found that depths less than 1.5 times the tunnel diameter resulted in surface settlement above the allowed limit of 25 millimeters, making tunneling at those depths inadvisable. But the same study revealed that going deeper creates its own cost and structural spiral. Construction costs are highly dependent on the station depth and the distances between stations. Meanwhile, research published in Scientific Reports, Nature, on deep buried tunnel linings confirmed that after deep underground excavation, the three-dimensional stress state of surrounding rock undergoes complex changes, including stress unloading, concentration, and deterioration of mechanical properties. In plain language, the rock itself starts behaving differently the deeper you go. It creeps, it flows, it pushes back in ways shallow tunnels never have to deal with. This is why modern urban metro systems are almost universally optimized for the shallowest feasible alignment, to reduce cost and improve passenger access, unless unavoidable constraints force them deeper. We don't build deeper subway tunnels, not because we lack the drills or the ambition. We don't build them because the mathematics of pressure and geometry sets an absolute limit. The deeper you go, the thicker your walls must be. The thicker your walls, the less tunnel you have. And at some point, the numbers simply stop working. It's not a failure of technology, it's a hard constraint baked into the physics of how solid matter behaves under pressure. Every subway train you ride is moving through a tube that exists in a careful negotiation with the earth pressing against it from all sides. Engineers calculated exactly how thick the walls needed to be, and left just enough room for the train. A few more meters down, and there would have been no room left at all.